Thank you. Appreciate it. Thank you all for having me. It's a pleasure to be here. Let's put an end to accidental breaking changes. Some of you might recognize me as the maintainer of cargo-semver-checks, which is a tool that this talk is about. And I also maintain a package called Trustfall, which is a query engine that powers cargo-semver-checks, and we're going to see a little bit more about later in this talk. I also write a blog that has all sorts of interesting and cursed code on it. I figured out a way to cause a major breaking change by adding an import in a Rust program, which is not something that one would expect would happen. And I also write a variety of educational and interesting Rust content, like the definitive guide to sealed traits in Rust, which is something that was necessary in order to make cargo-semver-checks possible and work correctly. So please check out my blog if this sounds interesting. But one thing that is also important to know is that, like many people at this RustConf, I ship major breaking changes to production. And in my defense, I didn't realize it was breaking. That is a theme that you're going to keep seeing on and on in this presentation. I didn't mean to do this. This is just something that happened, and I found out about it when a frustrated user opened an issue on GitHub to let me know about it. This is the thing that we're trying to prevent. Let's talk about how to do it. This talk has 3 sections. In the first part, I want to convince you that Fearless Cargo Update is a magical experience that we should all wish to exist in our lives. Then second, I want to show you why we are failing at this despite everyone's best efforts, why it's impossible to prevent SemVer accidents by hand. And finally, I want to tell you how cargo-semver-checks can fix what we humans by ourselves can't do, how automated linting can prevent SemVer accidents. Let's dive right in. Fearless Cargo Update is magical. Here's me running cargo update in cargo-semver-checks itself. As you can see, tons and tons of our packages seamlessly got updated, and this pull request got merged, everything was seamless. It was a lovely experience. What this means is that cargo-semver-checks got massively better. We got the benefit of a ton of security patches, bug fixes, performance improvements, new functionality. Everything is better off. And most importantly, we benefited from countless hours of very expensive maintainer's competence that was invested in every one of those packages. This is stuff that I didn't need to be an expert in because I could outsource that competence to someone else. This is lovely. Magic. The way that this works is because of semantic versioning. Semantic versioning is a way for maintainers and our tools to communicate with users and their tools. We normally think of versions as containing 3 parts. Major.minor.patch. And the convention is that when we're making an incompatible change, we bump the major version number. Now, Rust is a little bit special because we ignore leading zeros in versions. So just like 1.0 to 2.0 is a major bump, so is 0.1 to 0.2. So 0.x releases also have SemVer obligations in Rust. This is a little bit unusual compared to most other programming languages. And most importantly, this is how Cargo knows what's safe to upgrade. When I run Cargo Update, it will consult the index and take a look at all of the dependencies in my project and see if there is a non-major bump that it could upgrade my project to. And that is what it will include in the log file. So without SemVer, Cargo Update just doesn't work. Now, Cargo Update is a magical experience, but it's also quite scary. We've probably all experienced this at some point. SemVer-Breakage is a thing that happens and happens and happens and happens in the Rust ecosystem. This is not an isolated experience. And when one of these instances of breakage happens, a lot of people are affected. Every entry in this list is some frustrated user having to take action to undo breakage that affected their project. They didn't sign up to do this work. This work just happened upon them because of accidental SemVer breakage. The right way to think about this is not just that this is frustrating, this is also very expensive. Because this is tons and tons of people that had to take time out of their day to fix something that they didn't intend to break. That sucks. I'd like to convince you that accidental breakage is not a trivial matter. It costs the Rust community tens of millions of dollars per year. Here's my math. SemVer accidents by themselves are very expensive. They send maintainers scrambling.
They have to triage and yank versions and make patches and republish. All of this stuff takes away time that they could spend doing literally anything else that would be more valuable to the community. All of that is them working really hard just to return back to square one, to make their package work as well tomorrow as it did yesterday. This is not productive work. It's also very bad for users. Users are super frustrated. If I run cargo update, why is it my job to fix something that I didn't break? So I'm also working very hard as a user to return back to square one. This is not productive for me as a user either. We also have community-level harm downstream of these effects, because what we're teaching users when cargo update is something that is scary is that they shouldn't update. And when users decide to not update, what that means for us as a community is that we're all putting up with much worse software than we could have been. We're all delaying security patches, bug fixes, performance improvements, and so on. Our software is worse off. But it's not just the breakage that is expensive. And all of this is making everyone worse off at a huge cost to everyone. So we're all frustrated and we've all wasted a whole bunch of time. But it's not just the breakage that is expensive. The experience of cargo update being scary is costly by itself. If you've worked at a large enough organization, you probably had a larger security team that had a bunch of security policies and some very expensive SaaS tools, all just to make sure that you're fully patched and you're not vulnerable to any known vulnerabilities. Well, most of those security patches don't come in major bumps. They come in minor or patch bumps. And instead of having very expensive processes, people, and tools to help you update those dependencies first, just in time when a security patch needs to be applied, it would be so much easier and simpler for all of us if we could just cargo update every day and know that we're always running the latest software with all of the latest and greatest security patches. And finally, when cargo update is expensive and I worry about my dependencies breaking me, I'm going to want fewer dependencies. I'll be more incentivized to reinvent the wheel and rebuild functionality that already exists just from the fear of what if I get broken by one of these dependencies one day. But when I have more software that I'm responsible for, I'm responsible for more software. And that by itself is expensive, because now that is software that I have to maintain that I would not have had to otherwise. So that makes all of this kinds of breakage extremely, extremely expensive for our community. So on one hand, Fearless Cargo Update is this lovely experience, but we can't build skyscrapers on shaky foundations. So we need to do much better at semantic versioning if Fearless Cargo Update is going to be a thing in our lives. So why do we keep breaking it despite our best efforts? Nobody wins, and yet this thing keeps happening, so something's up. I really like this particular issue because it gives away the game. Nobody decided to break the entire ecosystem that day. This was just an accident that happened. It was a stochastic, unfortunate event. We ran a study with cargo-semver-checks that showed that more than 1 in 6 of the top 1,000 most popular Rust crates have accidentally broken semantic versioning at least once. Now, what does this mean? It means that these packages published a major breaking change without making a corresponding major version bump. And if that is something that happens in the top 1,000 crates, how do you think the rest of us are faring? If this is a problem that even our most experienced maintainers are having, this is not something that can be solved by just being more careful or learning more about the rules, right? This is not malice, incompetence, or carelessness. Clearly something else is at work. Another way to slice the data that we accumulated is that if you look at the top 1,000 crates, on average, there was 1 to 2 breaking releases per week. Now, that doesn't necessarily mean that if you depended on all 1,000 of these crates, your project would be broken once or twice per week, right? If a piece of the API gets broken, you only get broken if you happen to depend on that particular corner of the API. So that makes cargo update a very interesting experience. I've been calling it Rustation roulette, because you run cargo update, and then you figure out whether you got lucky or your project blew up. That's obviously not a fearless experience, so that's not what we want. And in order for us to build some empathy about why this keeps happening, I'd like to walk you through a couple of examples. The first one is super straightforward. We have a crate that has a public function at top level called example, and one day that public function just gets deleted. right? Super straightforward, obvious breaking change, and if we run cargo-semver-checks, it will tell us as much. It will say this function is missing, it can't be imported by its prior path, and it's the example function on line 1 of this librs file. And now you're probably thinking, I don't need a tool for this. This is super obvious. 55% of the breakage that we discovered was this kind of thing. A public item that used to exist in the API and then just disappeared without a major change. Now, you'll be surprised to hear this because obviously, I mean, a deletion of a public item is always a breaking change. So like, you'd clearly catch this every time, right? Well, as it turns out, that is not true. Here are a couple of examples. In this first example, we have a public function. It just so happens that it's in a private module. And because it's in a private module, nobody could import this function. So it doesn't matter that it's public. Nobody could be using it, so deleting this function completely, not a breaking change. Here's another sneakier example. Here we have a public function inside a public module, but that module is marked doc_hidden. Now, doc_hidden is an attribute that we use to indicate that something is not intended to be public API. It's most frequently used by crates that expose some macro functionality. When a user crate uses a macro, that macro expands to some Rust code that lives in the user's crate. But a lot of the time, it needs to do something fancy with the crate that defined it. And in order to do that, it can only access the public code of that crate. But the macro internals are not themselves intended to be public API. So we mark the macro helpers as doc_hidden. That means that only the macro is intended to use that public functionality, and nobody else is expected to use it. And because you're sort of warned that this part of the crate is not public API, deleting or changing that example function inside the doc_hidden module, not a major breaking change. But you might be thinking, okay, if the module is doc_hidden, I'll ignore it. Everything's safe inside. Well, as it turns out, that's wrong too. In this case, we have a re-export of that function from inside the public doc_hidden module. And because the function is re-exported at the top level without doc_hidden, users can import and use this function without touching any doc_hidden code. And that makes it public API all of a sudden, even though it was defined inside a doc_hidden module. So as you can see, even the simplest possible example is full of edge cases. That is why we humans keep messing this up. That is why we need tools like cargo-semver-checks, because cargo-semver-checks will get this right, and we humans will not. Here's a slightly more involved example. In this case, we're going to take a trait that already existed and we're going to extend it with some additional functionality. Our trait is called batch iterator. It's similar to the iterator trait, but it allows us to request multiple items at a time in a batch. So this next batch method takes a usize argument that is a target batch that we would like to request, and we get a vector of items back at a time, assuming there's anything to produce. And let's say that we've noticed that after using this trait for a while, a lot of our batch iterator implementations are particularly optimized for a specific batch size, like 8 items at a time is particularly efficient for some reason. So we say, great, we want to extend this trait. We're going to add an associated constant called best batch size. Now, obviously, we have a bunch of implementations of this trait, and so we want to be very careful to not cause a breaking change. So what we're going to do is we're going to define it as an option of usize, and we're going to supply a default value that says none. That means that any existing implementation of this trait will inherit this none value for the option unless it wants to provide something else. If we didn't do this, then any trait implementation that did not supply a value for this constant would be immediately broken. So great. We supplied a default value, avoided that breaking change. We're being very careful over here, so we're good now, right? No breakage? Any guesses? Yeah. Here's the trait that we were modifying being used in a downstream crate. And here's this interesting keyword that says we're using it as dyn trait. That means that this trait needs to be what's called object safe in Rust. Now, not all traits are object safe. But do you remember the exact rules for when a trait is object safe? Yeah, me either. I mean, I learned about this when cargo-semver-checks caught something that would have been a breaking change for me. Running cargo-semver-checks, though, we see that we have accidentally broken object safety. Cargo-semver-checks says this trait is no longer object safe. It can't be used as dyn trait. And again, it tells us that the problem is batch iterator on line 1 in the librs file. The problem here is not just that we broke dyn trait. The problem was that this was not an intentional decision. We were considering adding an associated constant for very reasonable reasons. We were being very careful about it, but at no point was there a decision point where we could have said, aha, are we going to break dyne trait? No, that just was not on our radar at all. And this is how accidental breakage happens in the real world. This isn't obvious. And more than 25% of the detected breakage in our study was some kind of item being added and that causing an accidental breaking change downstream. Now, there are a variety of other kinds of breakage that cargo-semver-checks could detect that came up in our study. And these numbers are approximate. They're intended to give you a qualitative sense, not necessarily be a firm quantitative thing. So more than half is deletions, about a quarter is additions, about 10% is auto traits like send and sync, about 5% is signature changes, things like functions no longer being const or becoming unsafe and so on, and 5% is sort of everything else that we didn't more precisely classify. So great, clearly we're not going to prevent these kinds of SemVer accidents by hand, so what's the solution? The solution is cargo-semver-checks. Here's how it works. You run cargo-semver-checks, and then you publish. It's a two-step process. Cargo-semver-checks is designed to not have false positives. Any false positive that exists is a bug. So it's intended to be used right in front of cargo publish very easily. It will automatically detect the version bump that you're making, and it will scan for API changes that are inappropriate for that bump. And it's actually planned to become a first-party part of the cargo publish command itself, so that one day when you run cargo publish, cargo-semver-checks will be right there with you. This is actually an explicit project goal, and I'm thrilled to be able to contribute toward it. Cargo-semver-checks is also very widely used and loved. If you already use Rust, you're already depending on a ton of crates that already rely on cargo-semver-checks for their breakage freedom. Cargo itself uses cargo-semver-checks to publish, as do some of the biggest crates like Tokyo and Hyper and Pio3 and Russell's and so on. And some of the biggest tech companies also use cargo-semver-checks for their open source projects. Now, you can see this is a user testimonial that was completely unprompted when one of those users discovered that they were going to make an accidental breaking change in one of their packages. It's a lot nicer to discover this stuff in CI than to discover it when someone opens a GitHub issue in your project. The way that cargo-semver-checks works is it takes a look at your previous release, what's currently on crates.io, and compares the API against the new release that you're about to make. It checks a variety of different things, like are all the public functions still there? Are all of the traits that used to be object safe still object safe? And about 90 other things. And like I mentioned, false positives are bugs. They do happen some of the time, but most of the time cargo-semver-checks has a very good idea of what it's talking about. To give you a sense of what those 90 lints look like, this is some screenshots from our GitHub project that I took recently. Except, this is not even a complete list, because by the time I took these screenshots, it was already out of date. We'd already merged some more lints. So this means that cargo-semver-checks won't catch everything today, but if your favorite lint isn't there, you could contribute it, or you could just check back in next week, and it's possible someone else has already added it. You might be thinking right now, how does all of this work? How can I trust it? Well, it's a little bit tricky. If we just scanned Rust source code, that wouldn't be enough information for us to detect whether something is a major breaking change. You noticed from the previous example that the object safety breakage, we never wrote din trait anywhere in that definition when that breakage happened. And so clearly, Rust source code is not enough for us to SemVer check. In an ideal world, we'd love to use internal compiler APIs, because the compiler definitely knows about object safety. But those internal compiler APIs are extremely unstable. They change from one nightly to the next. And that is not something that we want to do, because the classical way to rely on internal compiler APIs is to tell our users, hey, please install this specific nightly and then run cargo-semver-checks. And that would be kind of an unfortunate user experience. Instead, every cargo-semver-checks release supports a wide range of stable and beta Rust releases. So how does this work? The secret is something called rust.json. This is a machine-readable representation of the same information that rust.doc produces in an HTML file in docs.rs. Now, the existence of this format is something that has been a fact for a very long time, but this format is still unstable. It has all of the information that we need, like object safety and so on, but its format changes on the order of once a month and sometimes more often. So we still aren't completely free of this problem of what happens if our input breaks. The key observation to make this work is this. If we were able to write our lints as declarative queries, then changes in the underlying JSON format shouldn't matter, because our declarative sort of business logic is not necessarily tied to the underlying JSON format. And in fact, that's exactly what we do. The current cargo-semver-checks supports everything from Rust 177 to current beta. In practice, that means that we support everything from RustDoc 28 to 33 and everything in between. And at the very top of the stack, we have cargo-semver-checks. The thing that connects these two is the Trustfall query engine. Now, what this means in practice is that the top half of this diagram is all about business logic. It cares about SemVer and breaking changes and so on. And it runs a glorified for loop over a bunch of declarative queries. For each query, if the query produces some results, they get printed to the terminal because that is a breaking change that was discovered. In the bottom half of the stack, there's nothing about SemVer. There's nothing about breaking changes. It's all about figuring out how to adapt the RustDoc JSON format into the declarative schema that is necessary to drive all of those queries that we'd like to run. So we figure out how to compute those results. We have no idea what the intended meaning of all of those queries and results that come back are. And in order to give you a bit more of a taste of what this looks like, I'd like to walk us through the public function got deleted lint that we talked about earlier. I want to show you the exact lint query that exists in cargo-semver-checks today. Now, this isn't intended to be a deep dive into the Trustfall query engine, so I'm not going to spend too much time talking about the syntax and the various operators and so on. And instead, it's intended to just give you a peek behind the curtains so that you can decide if this is something that you're interested in digging into more. And I've put some more links in the Discord you might have seen if you're curious to dig deeper. The rule for the public function got deleted lint is a little bit involved, so let's walk through it together step by step. This is the query that we're going to run. It looks at a pair of different versions. It starts with the baseline. That's what's already on crates.io. And it says, find all functions inside the baseline that are public, because private functions can't cause breaking changes, that are importable publicly, so that another crate could have imported it and used it. This makes sure that we don't have, for example, a public function in a private module. We want to make sure that when we import them, that import is public API, so it's not doc hidden on itself on a module and a parent and so on and so on. And then we'd like to look up the function that is at the same import path in the current version of the package, the one that is about to be published. If we manage to find it, great, not a breaking change. If we don't manage to find it, if the same import name in the new crate no longer satisfies the above, it's not public, it's not importable, it's not public API, something or other, we found a major breaking change. So we say aggregate the number of matching functions in the current version of the crate and count how many of those exist and then filter equals to 0, right? So the corresponding function does not exist in the new crate. That's it. That's the whole lint. So as you can see, this is not something that is rocket science. In fact, I haven't written a lint for cargo-semver-checks in almost 2 years. Almost all of the 90 lints that cargo-semver-checks has today were written by people who are still in high school, still in college, or within a couple of years of graduating for the most part. So this is something that community contributors are able to make, and the entire community is better off for it. But it's also interesting to talk about what isn't mentioned in this lint, because a whole bunch of static analysis had to happen to let us figure out which import names are valid for that function. That's not part of the lint. A whole bunch of optimizations needed to happen because there exist crates that have more than 400,000 items apiece. If we ran that in a naive way, that wouldn't work. There are no optimizations that are mentioned in the lint. And obviously, there's all the relevant details of the JSON format because we have to support a range of different versions. None of that was in the lint either. So obviously, there's quite a bit of depth here, and if there's something you'd like to talk about more, please find me after the talk or in the Discord, and I'd be happy to point you to more resources and describe how all of this works. But by this point, I hope I've convinced you of a few things. One is that Fearless Cargo Update is great. It's something that we should all want to experience in our lives because it makes everyone better off. Second, Accidental breakage is very expensive to all of us, to the tune of tens of millions of dollars per year just in the Rust ecosystem. We should aim to make that number go down, not up over time. And finally, it's a lot better to discover breakage in CI rather than to discover it when somebody opens a GitHub issue to tell you that you broke your crate. Everyone is better off when breakage is found sooner. And cargo-semver-checks is how we make that happen. It won't take tens of millions of dollars per year to fund cargo-semver-checks so that we can get the number of breakage to be far lower than what it is today. So if I've convinced you of all of this, there are a few things that you could do to help. First, you could contribute code and lints to cargo-semver-checks, and that would be amazing. There's a lot of functionality that cargo-semver-checks doesn't currently have, and it should. Second, you could help fund its development. We have GitHub sponsors, and every dollar contributed really goes a long way. And finally, especially if other people depend on your crates, please use cargo-semver-checks. It will save both you and your users a lot of headache. Thank you so much for your time. It was a pleasure to be here.